Thank you. Thank you for a chance to speak here. So this is a talk on, well, derived Rham cohomology. This is a cohomology theory for algebraic varieties that sort of naturally comes from derived algebraic geometry. And I want to explain what it looks like. For the sake of motivation, I want to start with first recalling some more classical material, namely this theory of algebraic Rham cohomology. So I'm going to give myself a smooth algebraic variety over the complex numbers. If you want, you can reduce yourself to the affine case for everything I'm saying. So you can think of x as being cut out inside Cn by a bunch of polynomial equations. And then the smoothness condition corresponds to the fact that the matrix of partials has maximal rank everywhere. So on this variety, there is a natural complex. And this is the algebraic de Rham complex. So it looks like so. So it's OX in degree 0. This is the sheaf of functions. It's omega 1 in degree 1, omega 2 in degree 2, and so forth. Except everything here is happening in the algebraic category. So I only work with algebraic functions and their derivatives and so forth. And once again, in the affine case, you can really think of this as a complex of abelian groups. And the fundamental theorem about this object, so the cohomology of this complex is called algebraic de Rham cohomology. And the fundamental theorem about this is a old theorem of Grothendieck. And it identifies what the cohomology of this complex is. It says that the cohomology of this complex, so here I'm implicitly working in the Zariski topology, is isomorphic to the Betti cohomology of the underlying topological space. With coefficients in the complex numbers. So I'm going to just call this, give this object a name. So just an easy example of how this works. Let's say x is gm, by which I mean c minus a point. And I'm going to think of this algebraically, so I'm going to think of this in terms of its ring of functions. So the ring of functions is just C adjoint to one variable t and its inverse. And so the left-hand side, the de Rham complex, is just the cohomology of the following explicit complex. There's one generator in degree 1, and you can think of it either as dt or dt over t. It doesn't matter because t is invertible. And the right-hand side is the analytic cohomology. Well, analytically, it's homotopic to a circle. So it's just the cohomology of a circle. And so that's an example of the theorem. The generator in H1 corresponds to dt over t up to certain factors. But that's how this theory works in practice. The way Grothendieck proved this theorem is via resolutions of singularities. So Hironaka has a theorem that every variety can be resolved. The singularities on arbitrary varieties can be resolved, and open varieties can be compactified in a nice way. Nowadays, due to some recent refinements of de Young's theory of alterations, it's actually possible to avoid using resolutions to prove this. But that's not what I want to talk about here. The consequence I want to emphasize is that this gives a purely algebraic definition of an analytic object. And therefore, you can sort of start playing with it. So for example, if your variety was defined over a subfield of C, such as the field of rational numbers, which, for example, is the case over here, then this complex on the left also comes from a rational vector space. And therefore, you acquire some sort of additional arithmetic structure on the left-hand side, which is quite useful in Hodge theory. So that was my very quick overview of what the theory of algebraic de Rham cohomology is. And the question, which is going to motivate the rest of my talk, is the following. So what happens if x is singular? The complex I've written down still makes sense, but it does not compute the right invariant. One can write down examples where it just has the wrong cohomology. And the reason for that essentially is omega 1. This is just a sheaf. It's no longer a vector bundle, and it doesn't have sort of good properties. So the answer to this question is well known. There are several answers, in fact, and I'll just tell you one of them. So historically, I believe the first version of the Rham cohomology for singular varieties is what is now known as Hartshorne's theory, or crystalline cohomology. And it's sort of predicated on the following picture. So here's a typical singular variety. It's a nodal curve. There's one node. We know that it's the Rham well, in this case, it's actually cheating, but let's try and approximate this using something smooth. So Hartshorne's idea was simply that you take a little tubular neighborhood of this variety. It does not change the topology, but now because you've fattened it up, it's actually smooth. So this computes the right cohomology. So here's what I mean more formally. So let's say X is any algebraic variety. I put it inside something smooth, assuming that I can. Like, for example, in this picture, I put the plane and the board, which is smooth. And I define y hat, which is an algebraic object. It's a formal completion of y along X. So this is the algebraic version of a tubular neighborhood. And then the theorem, which in print, I guess, is due to Hartshorne, but is independently due to a lot of people, I believe. Professor Dewey, Herrera, Lieberman, maybe someone else I couldn't track down. And it says the following. So it says that the cohomology of this formal object with coefficients in its Rham complex computes the right thing. So once again, this is a purely algebraic construction. So it is an algebraic Rham theoretic way of computing Betty cohomology. One slightly dissatisfying feature is that it involves a choice. So I have chosen a specific smooth variety to put my X in. And the answer doesn't depend on the choice, but the construction does. And it would, of course, be nice to have a theory that's independent of the choice to start with. And one can do that. Crystalline cohomology provides exactly the formalism to do what I just said. So in a sense, instead of picking a single y, you quantify over all possible y and show that the answer doesn't change. So you get a well-behaved cohomology theory. So that's the classical answer to this question, and in some sense, it's quite satisfactory. There is another answer, which I'm not going to discuss, which comes from the theory of cohomological descent and mixed Hot structures. So you can take your singular variety X, you find some sort of a resolution where the terms are smooth, and then approximate the cohomology of X in terms of cohomology of the resolution. And because you can do Rham cohomology on the smooth guys, this gives you a new complex on your singular variety that is sort of Rham in nature and yet computes the right invariant. But once again, that's not what this talk is about. Instead, what I want to talk about is a slightly newer answer to this question, which is a derived answer. And to motivate this, I just want to tell you that so the problem with Rham cohomology for singular varieties was that omega 1 was not locally free. It was not a well-behaved object. So one candidate for producing a good theory is to replace omega 1 with a much richer object which does actually behave correctly. And that's what this is about. So if I give you any algebraic variety X over the complex numbers, there is a construction which is due to Lucy and builds on work of Quillen and Andre. And it produces a complex of coherent sheaves on X, or quasi-coherent sheaves on X, instead of just a sheaf. And so conceptually, it's best to think of it as living in the quasi-coherent derived category, but you can ignore that. And it has the property that if X is smooth, then it computes the right thing. So if X is smooth, this gives you the right answer. And if X is singular, it has non-trivial higher cohomology, and this cohomology has some information about the singularities of X. And using this object, one can define a new complex, which is the derived Rham complex. So I'm just going to define it for you. It's just, you take the definition of the Rham complex and replace omega 1 with L. So so it's this object. And to make sense of it, one has to do a little bit of work. It's a priori a bicomplex, and there's some choice in how you totalize it, but it's sort of technical, and I don't really want to get into it. Let me just say that it's a very specific object. And once again, if X is smooth, because Lx is omega 1, this is just the usual de Rham complex. And so the theorem about this object is the following, which answers the question. The hypercohomology of this complex always computes Betty cohomology. So this is a different way of computing de Rham cohomology, coming from this cotangent complex, which is naturally sort of more of a derived object. And it's still computing the right thing. I want to point out two things. So the first one is if you restrict yourself to a setting where X is close to being smooth in the derived world, which means that the singularities are pretty mild in the derived sense, which means that the cotangent complex is relatively small. And so after a lot of work, that amounts to saying that singularities are complete intersections. So if X has complete intersection singularities, then this is a theorem of Illuzi. The slightly surprising feature for me is that it is actually true in general without the complete intersection assumption, when there is no sort of hope of actually computing this particular complex on the nose. So. And the other remark is that I have totalized the bicomplex. It visibly has a filtration where I just sort of forget about a certain number of pieces. This oh, sorry. Thank you. Well, also have X. Right, so this has a filtration where I just forget about a certain number of pieces. And that filtration induces a filtration on this object. And this filtration is sort of a new filtration. It's not equal to the usual Hodge filtration. And I don't actually know much about this filtration yet. If sort of this stuff sounds kind of abstract, I want to just mention one corollary, which has nothing to do with derived schemes on the nose, and it's the following. So I'll say it in the affine case. So let's say X is spec R. R is a finite type C algebra. And then Betty cohomology is computed by the following explicit complex. So it's R in degree 0, R tensor R completed along the diagonal in degree 1, and so forth. R tensor R tensor R. And then the maps are sort of what you expect. X goes to X tensor 1 minus 1 tensor X. And then there's 3 maps here, and you take an alternating sum, and so forth. And so as far as I can tell, I don't know a way to prove this corollary without actually going through some of this derived stuff, and I'd be really interested in knowing if there is a way to do it. I should also say that in the smooth case, this follows from crystalline cohomology, or the way the machinery of crystalline cohomology gives you this description. But in the non-smooth case, it definitely does not. And one needs to do some extra work. So I'm almost out of time. And I just want to say there are certain problems about this construction that I would like to understand in my time here. One of them is whether I can realize derived de Rham cohomology as the cohomology of a certain sheaf on a site. Because I'm interested in proving a version of this theorem which allows non-trivial coefficients. And I don't quite know what the non-trivial coefficients should be yet. The reason I'm interested in that is actually I want to reduce mod p and do something mod p where there is a version of this statement. But I have no idea what the coefficients look like mod p. And I'd be interested in knowing the answer to that. And the second thing I would like to understand is this filtration. It's sort of the smallest filtration on de Rham cohomology that I know. It's smaller than the sort of Hodge filtration. It's smaller than the stupid filtration coming from the stupid de Rham complex. It's, I think, smaller than the filtration coming from the crystalline cohomology as well, although I haven't actually constructed an example yet. And I would just like to sort of know more about it. But I think I'll stop there.